science leads us to new knowledge, and new knowledge leads us to understand the world in a better way.
I like to say that the biosphere was the original World Wide Web.
There's nothing right about giving a machine the right to kill people.
To understand the world, the extremes will not do it. We need to look at the majority to understand what's going on.
Hello and welcome. I'm Anne Mossop from the UNSW Centre for Ideas. This event is one of our international conversation series where leading thinkers from around the globe join UNSW researchers to share ideas and inspiration. We're coming to you from UNSW Sydney campus, and I'd like to pay my respects to the traditional custodians of the land, the Bedegal people, and pay my respects to their elders, past and present. With us today are Robert Hazen and Martin Van Kranendonk, who's going to be talking about the early history and evolution of our planet. Our host, Martin Van Kranendonk, is the director of the Australian Centre for Astrobiology. He's a geologist and astrobiologist whose passion lies in understanding the early Earth and how and where life got started. He spent a good part of his life and career mapping ancient rocks in Australia, South Africa and Greenland, and has shared this knowledge with geoscientists from around the globe on his recent famous Grand Tour field trip around Western Australia, where he first met this evening's guest. It's my great pleasure to hand over to Martin as our host. Martin Van Kranendonk.
Thank you so much, Anne. And I too would like to take this opportunity to acknowledge the traditional owners of the land on which UNSW sits. And it's my great pleasure to introduce to you tonight's guest, Robert Hazen, Bob Hazen from the Carnegie Institution of Washington. Bob got his PhD in mineralogy and crystallography from Harvard in 1975. And ever since, he's been a research scientist at the Carnegie Institution for Science in Washington. He's also the Clarence Robinson Professor of Earth Science at George Mason University in the US, and is the executive director of the Deep Carbon Observatory. He's the author of 15 books on subjects from everything from supercomputing to black holes to the origin of life. And maybe most importantly, he's been married to his wonderful wife, Margie, for now 52 years, who is a science writer and published historian. I just want to bring in two other aspects of Bob's incredible life and career. He's been a professional trumpet player and played symphonic trumpet since 1966 until his retirement just recently in 2016, including with the International Philharmonic, the National Symphony Orchestra, and he's been the founding member of many symphonic and orchestral societies in his local area. He's also got an incredible collection of trilobites, over 2,000 specimens, representing almost 1,000 different species from 6 continents. And that collection is being donated to the Smithsonian Museum of Natural History with 50 exceptional pieces on display. It's quite a remarkable career in summary, Bob. And my first question, of course, is how do you do it all?
Well, hi, Martin, and thank you so much. It's such a pleasure to be with you at this event. Look, I've been just unbelievably fortunate. I know that from my childhood, where I had teachers who encouraged my curiosity, who never shut it down, who pointed me in the right direction, who served as role models. I had musician friends and scientist friends and collector friends and family who were just always encouraging. And so I had a very easy path, as it were. There were no obstacles, as there are for so many people, especially in these times, but around the world. And I recognize that incredible good fortune I've had has allowed me to pursue directions that I couldn't have dreamed of when I was younger. That's the life of science. You make it up as you go along and revel in it every day of the experience.
Yeah. I think that's a really good point, to recognize the fortunate capacity that we've had. Same for me, is to be able to really pursue our passions. But I'm interested, where did that passion, that curiosity come from for you? Is that something that was ingrained from birth? Is that in your genetic code? Or was that really fostered in you by your surroundings and by your parents and mentors?
That's interesting, Martin. I suppose it really is something that's genetic, because my mother wasn't a collector, my father wasn't a collector, but from the time I was little, I wanted to collect things. I wanted to organize them. I wanted to put them in some pattern. And at first it was stamps or coins or something. I always tried to learn about them.
Yeah.
But when I got to the natural world, when I started collecting fossils, when I started collecting minerals, I realized every one of these objects told a story. There was a history held in a rock, and you hold the rock in your hands, and that rock, it came from someplace. It was born at some point. It evolved in certain ways, and it's there for us to tell us these stories. And I became fascinated with those stories. And so that's been the story of my life in geology, where we tell stories of Earth.
Did somebody tell you those stories, or was it your mind that kind of created stories? You know, you see a lot of children enter their fantasy world. You see them in shopping centers and they're Superman, or they're flying through the air or whatever, right? They're in a different reality. Was your reality the color of rocks, the textures? Did you make up stories about them, or did somebody tell you a story that grabbed your imagination?
Wow, that's so interesting. You know, I think that in the early days when I was collecting minerals, when I had teachers who were kind of exploring with me, that aspect of telling a story, I would go to a famous locality where there were minerals like Franklin, New Jersey, or Patterson, New Jersey, or something like that. And you'd find specimens, and the stories were written down. When I got to college, I suppose in my early courses, the general geology courses, they too told about Earth and how it has changed over time and how it evolved. But as I got more and more into mineralogy, as I got more and more into the science that people were learning then, it got farther and farther away from stories. You'd be given a crystal, and when you see an object like that, what they would want you to do is measure its physical properties, its chemical properties, treat it as an abstract, idealized object that you could sort of measure and parameterize and do all those sorts of things, never thinking about, well, this crystal came from somewhere. That wasn't part of our science. In mineralogy, it was physics, it was chemistry, it was measurements, it was hardcore stuff. And for the first 20 years of my professional career, I made those measurements. I did them at high pressure. I did them in very sophisticated apparatus. I published lots of papers. Maybe 15 or 20 people would read each of those papers, you know.
I'd go off into the ether. Yeah.
It was very narrow and very focused, and that was paying my dues. That was what mineralogists did to become accredited.
It's your training. It's the background training that allows you to then step to that next level, isn't it?
That's right.
Yeah.
But when I went into the field with you in the beautiful Pilbara section of Australia, and I saw those minerals told a story. They weren't isolated crystals with idealized chemistries. Those were real living rocks, if you will. They had a history, and that's what we do when we go into the field. We try to tease that out, and to me that was much more exciting. So that's where my science has taken me.
Well, that's great. I mean, we'll probably get back to this a number of times, this idea about context. You know, it's so critical for the work that we do on studying life. How does it differ from just normal geology, and what place, what time, what habitat, all that sort of thing. How does that context then apply for mineralogy, and why is that important in developing the story of Earth, the richness of our planet's history?
Oh, when you think about our planet, it was so different at the beginning than it is now. We think in current models that Earth and other planets formed as gravity pulled together larger and larger chunks of the primordial material that made up our nebula. And gradually Earth grew. It grew to more or less its present size. It was very hot because of the gravitational release and radioactive elements that heated up the inside, and Earth probably largely melted, and then you formed a core of dense metal. You had a mantle of less dense rocks. You started forming this thin, brittle crust on the outside. You think about then, each of those steps, you're talking about forming solid phases. You're talking about forming minerals. And early in Earth's history, there were very few, very simple minerals, the kind that we might see if we went to Hawaii today or in some other parts of the world where basalt is being produced. But then as water and atmosphere and rocks interacted, as new kinds of dynamic processes began affecting those rocks, you got more and more and more complicated minerals, and new ways of forming minerals came into play. Ultimately, I mean, one of the biggest factors in diversity of minerals is life itself. We now realize, and this is incredible to me, a mineralogist who doesn't think about biology, but biology is absolutely fundamentally important in the mineralogy that we see on Earth. So
Hold on. Did you just make the ultimate sort of crystallographer view of the universe here, that life is actually just a crystal?
No, on the contrary, crystals are a manifestation of life. And so no, it certainly took minerals at some point and other chemistry to lead to the first life. And we don't know the details of that, but it's a chemical process that involved interactions of water and rock and atmosphere and organic molecules of various sorts. And whatever that was, you had a self-replicating group of molecules. But once that first living object occurred, it began to influence its environment. And that includes influencing the formation of minerals. And now we know that half of the mineral species on Earth can be formed because of living cells. Yeah. That's an astonishing statement. You know, when I first learned about mineralogy, minerals were separate. They were the antithesis of living things. But now we know that they're intertwined in such an intimate way that you cannot understand mineralogy without understanding life. And I don't think you can understand life without understanding the geology in which it forms.
Yeah. It's really about an exchange of energy between those two, right? Life, primitive life, needs an electron, and mineral surfaces are charged, and so there's that absolute interaction. But I want to get back to what is perhaps your largest contribution, which is one of the great stories in earth science that you've added to our lexicon, is about that idea of minerals evolving over time. And it's such a beautiful concept. And I want to ask you a couple of things. How did you come up with that idea? Because it was groundbreaking. Nobody had really thought about minerals changing over time. And then more abstractly, or maybe more poetically, how has that given you an appreciation of the length of time that our planet has been in the solar system, and how life is tied to that incredible journey of 4.5 billion years? It's a bunch of words. It's 9 zeros and a 4 and a 5. But how did your idea of mineral evolution come to sort of expand that almost personal attachment to time?
You know, Martin, it began because I, like you, are fascinated by the origin of life. And you keep thinking about what was Earth like 4 billion years ago when life arose.
Yeah.
And
it wasn't a blue ocean world. It didn't have white clouds. Didn't have giant continents. It was like a totally different place.
Yeah. So you think about that, and how could life arise? And so, as a mineralogist, I kept thinking, well, okay, maybe clay minerals played a role, or maybe sulfide minerals play a role, or maybe some other kind of mineral. And I was sitting at a party. It was December 6th, 2006. It was Christmas
can still
party.
remember.
A group of professors at George Mason, and a very dear friend and colleague, Harold Morowitz, who played a real role in thinking about the biochemistry and the energetics of how life might got started. We were sitting next to each other. We were drinking red wine. We were just chatting away. And Harold, as he did, he would say, "Oh, Bob, by the way," that's how he changed the subject. "By the way, do you think there were any clay minerals in the Hadean?" He asked me that question. Now,
right.
Okay, what does that question mean?
That's the sign of a fertile mind.
Because he wasn't a mineralogist. And what he was saying was that we think that life arose during this period of early Earth history called the Hadean. And many people are postulating that clay minerals played a very important role. And so what he was saying was, if clay minerals didn't exist in the Hadean, then those hypotheses can't be right. But what I heard as a mineralogist is, did mineral X exist at time Y?
Right.
And I had never heard anyone ask that question. And as I've gone around the world, I can't find anybody who ever asked that question. Nobody had ever asked, what was the first mineral in the cosmos? What was the first mineral on Earth? Was the mineralogy of early Earth the same as mineralogy today? And it just hit me. I mean, I cannot tell you what a revelation that question was. Isn't that incredible?
Well, you can still remember it so many years later. You know exactly the moment when it happened.
because it changed my life. It threw me into a mental frenzy. I don't think I slept for 48 hours. I started writing down ideas. What does this mean? Now, it took more than a year to write the first paper. And as I began working on it, I said, well, I really need someone who's an expert in meteorites. Better talk to Tim McCoy. Oh, I really need someone who's expert in aqueous geochemistry. Better talk to Dmitry Spredzensky. Oh, I really need someone who's an expert in Archean rocks, and I need Wouter Bleecker. And so I added authors, and eventually there were 8 of us on the paper, and each one had a specialty, and we put it all together and synthesized it and came up with this idea called mineral evolution. The idea that Earth has gone through a series of stages. We used a nice round number, 10 stages of mineral evolution going through Earth history, where at each stage some new process or event or characteristic came into play that changed or altered the near surface diversity and distribution of minerals. So there were many revelations as we began thinking through this. It just fell into place.
Yeah,
the ideas
as good ideas do. Yeah. Yeah.
The ideas were out there. You just had to synthesize them. So this paper synthesized these ideas. And the biggest punchline of that paper was that more than half of all the minerals on Earth are a consequence of living systems. That really that was the sound bite. That's the thing that captured people.
Pretty profound, isn't it?
Yeah. Became a part of the biological sciences as well as, and I don't just mean that your teeth and your bones and shells of organisms are made with minerals. We knew that, but this is much more subtle. It's that life changes Earth's environment in such a profound way that every aspect of the near surface environment, every aspect of geology and hydrology and mineralogy is influenced in ways that we really hadn't articulated quite as forceful a way, and now we know. And when you go to the Pilbara, when we go to the Pilbara and we look at those rocks, we see them in a different way because we realize that this is part of an evolutionary sequence. Yeah. And it's just giving us a glimpse of one stage of an evolving planet.
Yeah. It's interesting, when I hear you talk, I get very much the same emotions as I get through some of the research that I do. And I wonder if it's the same for you, that knowledge that life is tied to the planet so intricately. We talk about the interactions between, the crust and the atmosphere and the hydrosphere, but the biosphere is not just linked to water and nutrients, but it's linked to the crust in a fundamental way. And I think that's a little bit of what that revelation must have been like for you. And for me, the beautiful thing about that is it ties myself, my life, my generations, my history, my friends, everything to the planet I live on. It makes Earth more of a home. Is it like that for you?
Well, you see it everywhere. I go outside for a walk and I see trees rooted to soil, and the soil is making rocks. It was from the rocks. Well, the soil allows the tree to grow, but the tree's roots break up the rock to make the soil in which the trees grow. And even something as fundamental as our own bodies, the iron and the calcium and the other elements that are in our body, they were part of rocks. They used to be parts of minerals. And when we die, some of those elements will go back to being parts of rocks. And the cycle back and forth between living and non-living systems is perpetual. It's continuous. It's happened for billions of years. And we can begin to see our own lives and our own existence in a much grander context of the richness of the natural world, where we don't draw boundaries between physics and chemistry and biology and astronomy and geology. Yeah. It's science. It's the natural world. It's one epistemology, and it's one deeply moving aspect of our existence, because the only thing we have to deal with is in terms of reality, is our physical reality.
I'm really glad to hear you speak in this way, because I think one of the challenges that society faces is that science is kind of seen as removed from society. They're in the labs, they're doing things, they're measuring, they're doing all that quantitative stuff, but it's not actually about us or about the world. But when I hear you speak, what really comes to the fore, and I guess it's because I share a little bit that experience, is that intimate connection between science, life, history, all together. And I think that's a really important message to send to the general public, really.
So I had a good fortune about 30 years ago to be invited to be a university professor at one of the big state universities, George Mason University in Fairfax, Virginia, very close to Washington, D.C. About 30,000 students. It's a big place. And I was asked to teach a very large science class to undergraduates. My colleagues were appalled. My professional colleagues say, why in the world would you, with your opportunity to do unfettered research at a great research institution like Carnegie, why would you go to teach undergraduates? And not just undergraduates, but
With a degree of scorn.
These were undergraduates that were not going to be science majors. You know, they might go off and be businessmen or politicians or teachers or something like that. But what my colleague Jim Treffel and I did is we put together a course called Great Ideas of Science. And the book that accompanied is called Sciences: An Integrated Approach, where it was one semester course that taught science. Begin with the basic physics of motion and matter and energy and laws of thermodynamics and so forth. And you go into chemical bonding and the basic chemistry, and then you go into how do stars work, how do planets work, how does life work, and everything builds on it. It becomes one story of science. Teaching those undergraduates has so radically changed my own personal science, because I can no longer see a mineral. I can no longer look at this crystal and say, oh, you know, that's something I can take out of context. No. The crystal is only the beginning of an incredible network, a spider web, if you will, branching outward to all the different aspects of life and stars. The atoms were formed in stars. This crystal obeys laws of physics and chemistry because of the chemical bonding that goes on. And this crystal was born in an aqueous environment that was influenced by living creatures while it formed. I mean, it's all tied together. You suddenly see the world in this much more integrated way, and then you can tell the stories.
Well, and that's important for everybody to have. Not necessarily that they all study science or so, but that at least they're aware. And I think that's that's a wonderful thing to make people aware. If we can just go back for a second, I want to get a little bit more elaboration of your idea of the 10 stages of Earth history and the different colors. You know, if I sit in my office here in Sydney, I see a little bit of green trees, I see some concrete of the buildings, and I might see a splash of red as the streetcar goes by. Tell us about the colors of Earth and that evolution of colors in terms of your idea of minerals and life evolving over the time. Just give us a couple of examples of how you saw our Earth changing through your study of minerals.
So if you imagine looking at Earth from space 4.5 billion years ago, it would have been a black planet. It would have been covered by dark basalt, this heavy, dense rock. It probably cracks with bright red incandescence as lava was pouring out of various fissures and volcanoes. Fairly quickly, I think, maybe within 100 million years, maybe less, a substantial amount of water vapor came out of those volcanoes and started condensing on the land. And I think you would have started having oceans. And maybe at first they were blue, but fairly quickly, because of the very strong interaction of the water with basalt, you would have started getting rich in iron. And some people speculated you may have had green oceans at that point. You may have had, because of the atmosphere rich in carbon molecules, it may have had like an orange haze, much like we see on Titan today. These are speculations, but we know it was different from today. And then as you go forward, eventually granite, you'd start forming continental crust. This is the stuff that forms the land on which we live. And that rock is more of a gray color, so you'd start getting gray continents contrasting with the ocean. Boy, there was a huge change at the time when you had much more oxygen in the atmosphere caused by life. Here's the interaction between life and rocks. And then you start oxidizing things. And if you go to Karijini National Park in Australia, you see the deep red rocks. It's so vivid. Well, that's what Earth would have looked like. The land would have been bright red, much like we see on Mars today, for different reasons, I have to say. But you know, the idea of a red planet is not unfamiliar to us. And then you could have a period when Earth was totally covered in glacial ice. these are fluctuations of the climate from extremely hot to extremely cold. And if Earth gets cold enough, then the oceans freeze over from the poles all the way close to the equator. And so at that point, Earth would appear to be a white snowball. And then, of course, the evolution of green plants. And then you have the land turning green. And so these color changes are emblematic of how amazing the evolution of our planet has been, how it's gone through many stages, each one a consequence of what came before, each one leading to what comes next. So there's a kind of, as in any evolutionary system, there's a kind of contingency and a congruency that each stage follows.
Exactly.
And
Sorry, that was so beautifully put together by Stephen Jay Gould for biology. This contingency of biology is that once something is formed, you can get repeated cycles, but they're never the same because they're always leading in a forward path. What would Earth look like? What would Earth look like today if there was no life? Would it be fundamentally different? I mean, you talked about the green land plants, but let's say there was never any life on Earth. What might it look like now?
I think that's a really intriguing question. First of all, we wouldn't have an atmosphere rich in oxygen, although there might be ways you could form some oxygen.
But short-lived, right? It's just short-lived.
Short-lived. But it's very possible that if you didn't have a lot of oxygen in the atmosphere, you wouldn't have an ozone layer, and so you'd be bathed with ultraviolet radiation, which would cause all sorts of intriguing chemical reactions at the surface.
But it would be hard. It would be hard for life to live on that surface, wouldn't it?
It would be really hard. In fact, it was difficult for life to get a foothold on land until there was enough oxygen to protect the land from that harmful ultraviolet radiation. So you start thinking about causes and effects and cycles and feedbacks. I mean, that's what planets do. Yeah. One thing happens, and something happens as a consequence, and then you got all these things happening. One of the great uncertainties we have right now, as you know, Martin, is what's going to happen to the climate, the global climate, as we see change occurring. It's not the gradual change that worries me, increasing half a degree and increasing another half a degree, because
we've seen that in the past. Yeah.
Seeing that, and we'll be able to cope with it. But it's these tipping points where suddenly you get, instead of a feedback that dampens effects, if you get a feedback that accelerates what already happened. And people have talked about possibilities that this could happen on Earth today, as it probably happened in the past. A huge sudden release of methane from methane that's frozen into the rocks in the shallow subsurface. If this methane is suddenly released, that's a greenhouse gas that causes more warming. And then you get a positive feedback that could cause temperatures to spike much more rapidly than we're seeing today. So those are the things that, if I was kept awake at night worrying about our planet and as an evolving, Earth's going to be fine. Microbes are going to be fine, but human populations, it's if you suddenly raise sea levels not by 5 feet but by 50 feet, and every coastal area of the world is inundated with water, you're displacing more than 1 billion people. Yeah. And where do they go? What happens when Bangladesh disappears as a country? What happens when the Netherlands is just a tiny island?
And the fertile produce that they make as well. That's right. Yeah. Listen, you're touching on something that's, of course, very important to us, and we'll get onto other topics as well. But that idea of carbon being cycled at different scales, and I think for the general public, it's maybe worth just talking about sort of the natural cycle of carbon before we get on to that sort of rapid change. One of the best talks I've ever seen was by Professor Mike Searle, an Oxford University professor and professional mountain climber. He's climbed Mount Everest, I can't remember, but I think it's something like 12 times. Like, he's an exceptional human being. And I'd seen a talk when he came back from the Himalayas, and he just hot air ballooned over Mount Everest. Now, that is like impossible to do. He spent 45 days, like the entire season, waiting for one perfect day. But the most impressive, so he had these incredible pictures of the rocks of the Himalaya, giant crystals, you would have loved it, and then these beautiful scenic overviews of the entire Himalayan range. But his coup d'etat, if you like, his pièce de résistance at the end of the talk was he said, "Oh, I've brought something." And he reached into his pocket and brought out a little plastic bag with a rock inside. And he said, this comes from the top of Mount Everest. And it's a shelly fossil from a limestone on the top of Mount Everest. 8,800 meters above sea level, contains a shell from the ocean. How did it get there? And what does it mean to have carbon-bearing rocks at the top of the world?
So this epitomizes the carbon cycle, because what you're seeing is a limestone that formed as part of a coral reef, essentially, much like the Great Barrier Reef. So you have this limestone forming, but Earth has a very dynamic, if long-term process called
long-term process, yeah.
So you have reefs, but these continental masses are moving along with the continental plates, and sometimes when two plates collide and they carry with them coastal zones with coral reefs and so forth, you start getting mountains formed. They crumple together, they start raising and pushing together.
And how long does that take, Bob? What kind of time scale for the general person?
It's 100 million years to form a mountain range.
100 million years.
Form a mountain range like the Himalayas. And there was a similar mountain range, the tallest mountains in the world were once in North America called the Appalachians. And now they're eroded down. This was 300 million years ago, and now they're just eroded down to sort of
gentle hills,
beautiful hills and nothing you'd really call a true jagged mountain. But that's the cycle. We form mountains, we erode them away, we form new mountains, and the carbon cycle is tied up with this because carbon is moved by plates. Some of that carbon is taken in thick layers down deep into Earth, where it heats up, where it melts, comes back to the surface as volcanoes that spew out carbon dioxide into the atmosphere. And this was the main carbon cycle for millions of years. The principal...
Billions of years, yeah.
Billions. The principal motions of carbon has been subducting down, coming back up from volcanoes. It turns out what humans are producing now by burning and producing CO2 is it's 10, 20, 50 times more than the most active volcanoes that have been going on. So we are suddenly tipping this whole process, which was gradual, which was stately, which was well controlled, and we're skewing it by burning all of this buried carbon that was locked in the rocks. It was sequestered. It wasn't going anywhere. But when we burn coal, when we burn oil, when we burn natural gas, carbon that has been locked in the subsurface is suddenly brought back and put into the atmosphere.
So we're so you would say that, or you could say that we're really condensing the geological cycle by extracting materials and utilizing them in a way that nature had not done before.
The millions of years it took to make the coal that's buried underground is being reversed in a matter of decades.
Exactly. So I think that's important to understand, that telescoping creates these spikes that are outside of the natural variation. Listen, one thing I wanted to talk with you about as well, so many things, but you run the Deep Carbon Observatory. What is deep carbon? You've mentioned about subduction, but if it's down in the mantle, how can you see it? And what relevance does that have to our lives today?
Sure. So the Deep Carbon Observatory was really a large scientific program that was designed to understand the hidden 90% of carbon in Earth. Many, many people, for understandable reasons, have studied carbon in the oceans, carbon in the atmospheres, carbon in the shallow crust where we mine it for coal and natural gas. But there is a hidden carbon cycle that goes much deeper. That's some of the carbon that's subducted down deep into the mantle, carbon that may be present in the core of Earth, carbon that may be present in various sorts of minerals very far down in what's called the lower mantle. And we had no idea. There was almost no one who'd been studying this because it wasn't the main topic. And so when we went to the Alfred P. Sloan Foundation, who funded this for a substantial amount of money, it was a 10-year-long project with over 1,200 people in 50 countries that were involved in it, including many colleagues in Australia. This program was to try to characterize all the aspects of the carbon cycle and have a much bigger model of where things were going, because that's the baseline, Martin. That's if we want to say, well, what are humans doing today that's different? You really have to know for sure how much carbon is coming out of volcanoes, how much carbon is being sequestered by weathering on Earth's surface, how much carbon is going down in subduction zones. Is the amount of carbon going down equal to the amount of carbon coming out? It could be more, it could be less. We didn't know. And so this was a chance for us to have a global effort to study carbon and make this focus. So here's the baseline. And I'll tell you, that baseline is scary because it shows that humans are just completely overwhelming every other aspect of the carbon cycle. That what we're doing in the last century and a half is just unprecedented in Earth history. So that, that's something that, as we're making policy, as we're thinking about what sorts of actions government should take, and we should, as a society, take to should we care about global warming? Should we care about the carbon cycle? This is just scientific evidence that there is something fundamentally different about what we're doing.
Yeah,
so that's
enough.
where we.
Thank you so much. Listen, I noticed over your left shoulder, you've got some beautiful lithoprints of some fossils there, trilobites, and you've got this incredible professional life as a trumpeter, and we've talked about time. How do the three T's come together in your life? Trilobites, trumpets, and time. How did that happen?
Oh my! So it really represents the kind of richness I think that we all look for in life. I was very fortunate to have parents who loved music and played and sang and introduced me to music at an early age. And so I had that opportunity and I loved it and I got pretty good at trumpet. So I had an opportunity. I could have gone to a conservatory. I could have been a professional trumpet player. But I also had very good mentors. And what they told me and what I realized very quickly was true is you can be a very good musician on the side while doing science. But you can't be a very good scientist on the side while doing music. Science requires a kind of dedication and concentration and focus and facilities. But for a trumpet player, if you learn how to play well, then you can be what's called a freelancer. And I got to be, when I came to Washington, D.C., I got high on the list of the union trumpet players. And so when there was a job open at the Kennedy Center or the Opera House or something like that, I would get called and
Fantastic.
So I could often fit that into my schedule, partly because at the time I was doing research that had automated instrumentation. So it had to be checked every 6 hours, 7 days a week. Imagine this. So I lived just 2 minutes walk from the laboratory. And I would set up my schedule. So I would mount crystals. I would put them in this apparatus. It would take about a week to do an experiment, but you had to realign it every 6 hours. So I just religiously 7 days a week went there. But I'd have blocks of time where I could either go to a rehearsal or go to play a concert, and that was great. So it turned out I was very fortunate to have just found a sweet spot where I could do the music. And in terms of trilobites, I've always collected something. I collected minerals for a long time, but when I became a professional mineralogist, it really was a conflict of interest to be going to very famous mineral museums and getting specimens for research. You don't want to really mix your hobby with your profession in a way that there could be and minerals can be very valuable. And so I started collecting trilobites. I was fascinated by them, and there were some very great trilobite localities that I have access to. So and it just kept growing and just kept building the trilobite collection, and I studied it and I learned about it. And then when I got to a certain point, I said, this collection is too big and museums can't afford stuff like this. I mean, these were really fabulous specimens. So we donated the collection to the Smithsonian Institution, and now you can go there and you can see some fabulous specimens.
Yeah, beautiful. I'm looking forward to doing that at some point.
We donated them already. They're on exhibit, and I'll tell you one of my life's favorite moments was I went to where about 50 of my trilobites are displayed on a wall.
Yeah.
And there was a young boy, maybe 7 or 8 years old, and he was just going.
Cool.
And Martin, that was me.
That's what it's all about.
That was me.
Yeah.
That was me. When I was a 7, 8 year old, going to a museum, looking at the specimens, and I said, what better way to pass it forward than to give something that might inspire another young person to become scientists. And I've dedicated a lot of my time in the last years to promoting early career scientists, because that's our legacy, Martin.
I was going to ask you, there's a lot of challenge for people, and there are a lot of different, avenues for people to find careers and stuff. And one thing I've always found interesting is that it's very natural for children to pick things up and look and to start to collect. I mean, you see that for everything, whether it's rocks or butterflies or dirt or plants or bugs or whatever. You always see kids, that's part of our learning about the natural world that we're in. Of course, as we grow up more and more in cities, we're starting to lose that. But the people who do have that natural curiosity, what is the steps to keep them in that field? Because science, as you've mentioned today, and I think as many recognize, is so fundamentally important to our society. Good scientists making new discoveries that make our lives better. So keeping that natural curiosity for people, what's the secret there? Do you have any insights to that? Because you said you've taught to undergraduates, you've inspired young children. There's a gap, though, sort of in high school, where that link often seems to get lost in terms of allowing children's curiosity to then develop more fully.
And that's the problem with an education system where many of the teachers of science don't have the appreciation that it's about asking questions. It's not about memorizing answers. And so, to me, you need to have mentors. You need to have people like you and me who take students in hand and say, you've got great questions. Let's see if we can figure out an answer. The most exciting thing in science is not, I have an answer. The most exciting thing in science is to say, I've got a question.
That was that question that colleague of yours asked you about clays and the Hadean. Just that question. Yeah.
It's asking a new question. If you can come up with a question that no one's ever thought to ask before, you will be a great scientist.
And so who were your mentors? You've mentioned it now a number of times in your choice of trumpet versus science. I mean, everybody's faced with big questions in their life. How did you find mentors? Was it your parents, or was it close friends, or was it parents of friends? Where did you find that guidance?
Well, my parents played a strong role. My father was a brilliant musician. He could have gone on to a concert pianist career, but instead he got an electrical engineering degree and went into a more technical field. But I had a fabulous 8th grade science teacher, Wilfred Welsh. The mineral Welshite was named after him. He was a famous amateur mineral collector, and he took me under his wing and helped me find mineral localities and pointed me in the direction of where I could go. I had incredible teachers at university. In high school, I had chemistry teachers who said, go do independent projects and do this research and let's just study things. It was not memorizing the periodic table, which I think is a terrible thing to do to a child.
You can look it up on Google now.
Yeah,
you don't need to anymore.
It's not hard to find the periodic table. And I had David Wunz was my first freshman teacher at MIT. I went to MIT as one of the very few people who said he wanted to study geology as a major. They loved that because most people came to it later. But David Wunz I went on field trips with him. I was his field assistant, and he would just bound across the rocks. He loved the outside. He loved birding. He loved taking photographs. He loved the rocks. He loved everything. And his enthusiasm was just so infectious. And I said, gee, when I grow up, I could do this for a living. And I'll have to tell you a secret. Margie and I were walking in my field area just a week ago, and we turned to each other and said, what do you think we should do when we grow up? And we haven't decided yet. We haven't decided.
That's a beautiful thing.
We don't have to decide for a long time because it's just this exuberance of being able to study nature is wonderful. I was given that gift, and I've never lost it.
It is a gift, isn't it? Now, I understand that you've had another gift. You actually have a mineral named after yourself. Oh. Tell us a little bit about that mineral, because I love the story, and it's a perfect link between life and minerals. I just love it. Tell us about Hazenite.
I'm very proud of the mineral Hazenite. It's only known from one locality in the world, and that's a place in California known as Mono Lake, which is a very unusual lake. It's a hypersaline lake. It's got a very, very high concentration of phosphorus and some other elements. So high, in fact, that when microbes live in this lake, they can't survive unless they adjust their internal chemistry. And so one of the ways they do that is they excrete crystals. Crystals of an alkali phosphate, which is hazenite. So hazenite is essentially microbial poop. As my good friend Sean Solomon said, hazenite happens. But it's a biomineral. It's only known to be formed by microbes in this one environment, and I'm just thrilled that somehow the mineral that gets named after me is one that has such an intimate connection between the microbes and the rocks, and it's telling us about chemistry, and it's telling us how microbes adjust their environment to make it possible to live in these extremes where you wouldn't think it's possible to live. So that's my mineral.
That's
great. Do you have a mineral, Martin?
No, I don't have a mineral. I don't have a rock. I don't have an asteroid or a planet. No, I'm just little old Martin Van Kranendonk. But do you think there would be hazenite on Mars? Do you think there could be hazenite on Mars? No. Why not? Is that because there's not life, or there's not phosphorus, or there's not cyanobacterial poo, or there's not Mono Lake?
First of all, you need to have a lake. You need to have a lake that has extremely high alkali and phosphorus, much more than would be normal, because this is one of these places that sort of keeps evaporating. You keep concentrating things.
Well, we know on Mars there are some very, very salty brines that are even still existent. Yeah.
Phosphorus. But I think you'd form other minerals first. And when you think about why certain minerals form, you have to ask yourself, do you have the right chemical conditions for that mineral to form? And you also have to ask, would something else form first? Yeah. And there are other minerals, phosphate minerals, that would be much more likely to form in Martian environments. Things like apatite, where you have more calcium. There's very little calcium in the Mono Lake zone, but on Mars you probably would always have some calcium. But it's a good question. Right. I mean, you can speculate, but we're just beginning to learn about Mars mineralogy, and there are some surprises there. So maybe, who knows, maybe that's one of them. But so far, it's only known as a microbial poop.
Well, I guess we have to be honored by what comes our way, but I would be very honored to have a microbial poop named after me. Robert, thanks to you so much for your time. I know you're intensively busy. Tell us just a little snippet about your most recent work that you say you've been cramming to write this paper. You're just a few days away from finishing it off. Is it your grand opus? Is it your life's work, or is it? Tell us about it.
It's the next big mineral evolution paper that's taking what was a very qualitative story of 10 stages of mineral evolution in 2008. And saying, okay, let's go down and be absolutely rigorous. We have 5,700 known different kinds of minerals. How did every one of those minerals form, and when might it have first occurred? And let's put this on a timeline. Wow. And that's what this paper does. It takes a big data approach, but it involved months of building databases and spreadsheets and sorting through what could be as many as 200 different what are called paragenetic modes. That's ways minerals form. And they form in lavas, and they form in deep underground, and they form when ice freezes, and they form in dozens of different sorts of ways. Yeah, there you go, microbial. And so the idea was looking at every mineral, saying, how does it form? When could those formation mechanisms have occurred? And what was that timeline look like? And so this is a much more rigorous quantitative approach to mineral evolution. And that's what scientists do. We need to quantify. It's not just storytelling, but it's rigorous, reproducible, quantitative descriptions of the natural world. Yeah. Other people can examine and say, well, okay, I think you got this fact wrong, and then I think you got this interpretation wrong. And that's what drives science forward.
Absolutely. And I think it's an interesting point to leave it off. We're just about out of time. But one thing we've been trying to clarify for people in the general public is that, we hear so much opinion in the newspapers these days and online and on different forums, people's opinions, this opinion, that, and stuff. But science is not opinion. It's based on rigorous observations, your 20 years of measuring crystals, your big data approach like that. I think it's really important that that message gets across, that it's not your opinion versus my opinion. It's what the data says. And if I investigate that data and find an error, then that's how science moves forward. And that's a really important message, I think, to leave out there.
Absolutely. Our scientific facts have to be reproducible. They have to be independently verifiable. And that's the basis. If I can make a measurement, you have to be able to reproduce that measurement. And then we can talk about interpretations.
Yeah.
And that's what makes science sort of fun and creative. And then say, well, what's the next measurement we have to make to resolve between this hypothesis and this one?
Yeah.
And then we go out and we make the measurements, believing. We believe. We do have a belief. And that's that there is something that is true. Nature has a truth. And we are trying desperately to find what that truth might be.
Perfect. Bob, thank you so much. It's been a great honor and pleasure. We could keep talking for another couple of hours, I'm sure. And let's hope that international travel can recommence so that we can touch base and have another beautiful lunch like we did in Chicago at that restaurant with the ABSACON meeting, and maybe even travel into the field together. Thank you so much for your time.
Be safe, be well. Thanks so much for the chance.
Same to you. Godspeed.
Bye-bye.